Okay, so I think it's time to get started. So a few announcements before we start. So one thing is, so actually there's a lecture scheduled on December 26th, but I'm gonna do it on demand. So you don't have to come to this classroom, or you don't have to connect to the Zoom in real time. So just let's not just do it real time. So for humanitarian reasons. So I think it's inhuman to do a lecture on then that near the end of the year. I don't know how you feel, but so I actually I have to do a lecture on the next day, December 27th, so which I'm going to do on demand too. But anyway, so just look at the announcement about the exact format of this. So the lecture of this day. So it's gonna be a video. And the other thing is, so I have released answers for the some of the assignment and exercises, which are not necessarily the assignment, but for some Jupyter notebooks that contain some problems. So specifically 01 and 02 and 06, I just released answers for them. And here's a plan for today. So I'm gonna finish this the remaining part of the slide I was talking about 2 weeks ago, which is about how to get nearly peak flops, very good performance of a CPU. And I released another Jupyter notebook, which is going to become your next assignment you are supposed to submit. It is about how to make this matrix multiplication program fast using what you are learning now. So what you have been learning in the last couple of weeks and including today, using SIMD and a good understanding about instruction level parallelism. Okay, and hopefully you have plenty of time in this lecture, in this class today, working on this exercise starting today. Okay, so the slide I'm gonna talk about is this. So if you wanna look at in your computer, then you can do that. Right, so where is it? Okay, so I think this is the slide we left off the last time, but just to refresh your memory, the thing we've been discussing was the performance of a very simple code that looks like this. So doing X plus B, so X plus C actually in this slide. But essentially lots of FMAs, fuse, multiply, and add instructions, and investigate its performance. So the reason why this piece of code is particularly interesting when it's not so useful is that, so when you talk about the maximum performance of a processor, it is basically about FMAs. So the processor, the more specifically, most, if not all, modern CPUs are able to execute something like 2 FMAs, SIMD FMAs, every single cycle. And actually, there's no other way you can achieve this performance in terms of the flops. So I'm just using a code that does almost nothing other than repeating FMAs, right? So if this code doesn't perform, as very close to the peak performance. Nothing can essentially, right? So that's why we are investigating the performance of this simple code. And if we measure the execution time of this piece of code, what we discovered was it runs as fast as 4 cycles per a single FMA. And the reason was FMA instruction has something called the latency of 4 core cycles, which is that, so in order for this, for example, this FMA instruction to get executed, well, it obviously needs to wait for the input to become available. And if the input is made available by this previous instruction, then this instruction can start only 4 clocks after this previous instruction gets started. So this is what I mean by the latency. If this instruction needs an operand that is produced by this instruction, then the execution of these 2 instructions must be at least apart apart by the latency of this instruction. So this is the latency. So the important thing you need to remember is that if we do a computation like this, then this X is produced by the previous iteration. So it can not change the fact. So what is it? How close is it to the peak performance? So remember the peak performance is 2 FMAs every single cycle. But just compare it with this, only 1 FMA every 4 cycles, right? So it is actually a factor of 8 slower than the peak performance. And how to overcome this? So how to get closer to the maximum performance? So in generally speaking, get more performance. Well, so like I said several times, you cannot make this one any faster than 4 cycles per iteration or 4 cycles per FMR. You can only increase the performance or the throughput more specifically, which is the number of FMAs you can perform in the given amount of time by running multiple independent such computations at the same time. So more specifically, what I'm talking about so instead of just doing a single loop, instead of just doing a loop that updates only one variable like this, why don't you have just 2 or more variables to update within a single iteration? So just by looking at these 2 statements, you can realize that these 2 statements are independent, right? So this one does not depend on the result produced by this blue one, right? So it still, of course, depends on the result from the previous iteration of the same statement. But because these 2 statements are independent, the processor can run these 2 statements like this, right? So in the same amount of time, you can actually double the work you need to you are doing. And it in fact happens. So if you run this loop instead of this one, what happens is that it takes exactly the same amount of time, even though the amount of work you are doing doubles. So in this way, you can increase the number of variables you update further. like this. So I'm slightly changing the how the code looks. So instead of literally writing 8 separate statements, I'm just writing the inner the one iteration as a loop, updating this number of variables. So because I'm using the loop, the iteration is another loop, but it's essentially just doing, well, for example, if NV is 8, it's just doing 8 FMRs within a single iteration of this outer loop. So then what we hope will happen is something like this. So if we have, if we set NV to, for example, 8, what we are hoping to happen is something like this. And the reason why these 8 operations do not happen exactly at the same cycle is precisely because the processor had the limit of only being able to execute 2 FMAs per cycle. So it can execute only up to 2 FMAs in the same cycle. But if we have, for example, 8 independent X plus B loop like this, then yeah, every single cycle the processor hopefully performs 2 FMAs. So this is how you can get well, nearly peak performance. Well, when of course this loop itself is not very useful, but just for the purpose of understanding and demonstration. So you can play with something like this using the Jupyter notebook I gave on the last time, so PD07. So if I actually change the number of variables updated within within an iteration, then yeah, what happens actually looks like this. So this purple line indicates the number of cycles it takes per iteration. So like I said, if you increase the number of variables, the amount of work you're doing increases. Nevertheless, the cycles per iteration stays exactly at the 4 cycles, which is precisely the latency of a single FMR. And so in other words, in terms of the throughput, which is the number of FMAs you can perform in a single cycle, it almost linearly increases. So you almost linearly increase the amount of work you are doing within a single iteration, but the amount of cycles, the number of cycles a single iteration takes stays constant. So the throughput almost linearly increases up to a limit, which is exactly 2 FMAs per cycle. So in terms of the number of floating point operations per cycle, it is 64 single precision floating point operations. So two FMAs. So a single FMA for single precision floating point numbers performs FMAs on 16 different operands, right? And a single FMA is 2 flops, right? So 2 by 16 by 2 FMAs per cycle, so which is 64. And this is precisely the peak performance of this processor in terms of flops. So you can witness it by yourself by playing with the PD07 Jupyter notebook. So let me generalize what I've been talking about a little more. So this is, generally speaking, how modern CPUs. So aggressive superscalar processors operate. Which is that, so I think you know something about superscalar processors, like it can perform multiple executions, multiple instructions in a single cycle. But generally speaking, so how you translate it into the performance of your program, which is the very important part. So one thing is that instruction decoding, so fetching instructions from a thread goes much ahead of the actual executions of instructions. So each thread gives a sequence of instructions to the processor, right? But the instruction fetching and decoding generally goes much far ahead of the actual executions. And the actual execution of an instruction does not happen until, and generally speaking, happens as soon as its operands and execution resources become ready. It is something called out of order execution. So many instructions are already decoded in general. And the processor is actually watching, so which instructions are ready to get executed. So an instruction becomes ready to execute when its operand becomes ready and its execution resources become ready. And it is not constrained by the actual order of instructions in the instruction sequence. So having this in mind, so as a very crude, somewhat optimistic approximation, that the performance is constrained by only by the following two factors. So one is latency, like we have already discussed. So the latency is imposed by dependencies between instructions. So when an instruction needs an operand that is produced by an earlier instruction, then this instruction can get started only a few cycles, the latency cycles after the earlier instruction, right? So that's the latency. And the throughput. So you can increase the performance by having so many independent instructions that can be executed concurrently without waiting for some other instructions. But even if you have so many independent instructions, it is ultimately limited by the throughput. So it is imposed by execution resources of the processor. For example, the processor has only two FMRs, so execution units. The two execution units that are capable of doing an FMA per cycle. So the peak throughput of two FMRs per cycle now stems from the fact that the processor has only two execution units doing FMRs. So this is, well, generally speaking, this is the way you understand the performance of a particular workload. So first of all, dependency. So you impose in your program, right? So you do some calculation and the result is taken by another calculation. So this way you can make so many dependencies between computations. That dependency constraints how fast a particular computation can proceed. So it has nothing to do with the execution resources of the processor. No matter how many execution resources the processor has, so dependency dictates how fast a computation can go. And generally speaking, when you have dependencies, well, there's no way you can make this particular dependent chain of computation any faster. The only way you can increase the performance is to increase the throughput, which is the number of such computations that can be independently performed by the processor. But the throughput increase hits the limit at some point due to the execution resources of the processor. So this is precisely what you have witnessed in this very simple example. So I've been talking about so when I talk about the throughput, the only thing I was specifically talking about was this FMA throughput. So FM at throughput, so that the processor can execute up to 2 FMAs per cycle. But this is actually more general. So the thing you need to know is, so all instructions, whether it's FMA or not, integer instructions, jump instructions, load store instructions. So all instructions have their own throughput limits, well, just like FMAs. So FMA happens to have the throughput limit of 2 FMAs per cycle, but there are similar limits on all instructions, obviously. So they all stem from the same reason. So the processor has only so much execution resources. Some examples of recent Intel CPUs are like this, but primarily we only have to look at this one, Ice Lake SP, which we are using. So it has the throughput limit of floating point addition, multiplication, and FM adds of 2 instructions per cycle. For load instructions, it has actually the same limit. So that the processor can perform only up to 2 SIMD load instructions per cycle. The store limit used to be actually smaller. It used to be 1 per cycle, but in the most recent one, the restriction is somewhat relaxed to 2 store instructions per cycle. And typical integer operations have a much higher throughput limit. So at least in modern Intel processors, you don't have to worry too much about these integer operations happening alongside with floating point operations. So that the performance is in many cases not limited by integer operations, mainly limited by either floating point operations or memory access operations. So what this table tells you is, for example, if your loop contains, for example, 10 load instructions, then there's no way you can perform this loop faster than 5 cycles per iteration, right? So because the processor can execute only up to 2 load instructions per cycle. So no matter how independent they are, this loop containing 10 load instructions can run only as fast as 5 cycles per iteration. So the table or throughput limit of instructions can be used in this way to reason about. Well, so one thing is why this particular piece of code runs only so fast, and how to make it faster. And I vaguely categorized instructions into, for example, floating point addition, multiplication, FM at load store, and things like that. But you can easily imagine that all the instructions not specifically listed here are actually the subject of the same limitation. For example, there are so many instructions that somehow read data from the memory. They are broadly categorized into this load instruction because they are actually using, well, not very naturally using the same execution unit, which is something called the load unit. So all instructions are actually categorized like this, depending on what kind of execution resources they need, right? And a more formal or more technical understanding about this is something called the dispatch port, which I'll get into the next slide. So dispatch ports. So this is what the process actually looks like. So this is something called front end, fetching and decoding instructions, and sending these decoded instructions in something called a scheduler. But what is important in our discussion here is these what are called dispatch ports. And here you have execution units. And it may be difficult to see, they may be too small, but for example, each box describes the kind of instructions it can handle. For example, it says ALU, which is basically arithmetic unit. So doing integer arithmetic. For example, you have here FMAs, which is floating point multiply and add instructions. And there are only so many execution units. And each execution unit takes the operand to work on through something called dispatch ports. Right, so this is how superscalar processors are operating behind the scene. So each instruction, or more precisely in Intel's terminology, so one instruction may be decomposed into some smaller instructions, which they call micro operations or mu-op. So to be more precise, each micro operation or mu-op is dispatched to a specific execution unit through a dispatch port. So this particular processor has 10 dispatch ports. So it doesn't have to be universally the case, but generally speaking, each port can take only a single operation per cycle. And it can take a single operation per cycle, and it can take only a single operation per cycle. So, for example, by looking at this picture, so by realizing that there are 4 ports behind which they have ALUs, it generally tells you that, okay, this processor can execute up to 4 integer operations per cycle. For example, you have 3 execution units, so 3 ports behind which you can have FMA execution units. It actually tells you that it can perform up to 3 FMAs per cycle. But it may be contracting what I have been telling you about the maximum performance, which is about 2 FMAs per cycle. Well, the fact seems that these 2 FMAs execution units can take only up to 256-bit SIMD operands. So these 2 are combined to execute one 512-bit SIMD operands. And then there's another execution unit that is able to do 512-bit operations by itself. So the maximum throughput is still 512 bit SIMD-FMS per cycle. So you can reason about the capability of the processor by looking at this dispatch port organization. So to summarize, this dispatch port and execution units, even if they are very vague and abstract picture, but they can determine the throughput of all instructions that go to that specific port, and all in all, what is the throughput of the entire processor. So what the processor is able to do within a single core cycle. It is determined by this dispatch port and execution unit configuration. So theoretically, so with a destination ports of all instructions known somehow, and you are given all the instructions you want to perform within the iteration of a loop, then yeah, you can theoretically calculate what is the minimum number of cycles this particular iteration. So one iteration has to take, right? For example, if you have 10 instructions that need to go to this specific port, then the minimum number of cycles a single iteration takes is 10, right? For example, if you have 30 instructions that need to go either this port or this port, then the minimum number of cycles per iteration will be 30 over 2, which is 15. So this kind of reasoning you can perform to calculate the number of cycles a single iteration needs to take. But this is the general theory. So the processor has execution units and corresponding dispatch ports. And well, actually the processor specifies this instruction needs this dispatch port. This instruction needs this or that dispatch port. Now, based on that knowledge, you can, in principle, calculate the number of cycles and single iteration takes. But whether you want to do that is another question. So every time you have a loop you want to maximize the performance of, do you need to look into its assembly and somehow look up some sort of tables to know which dispatch port specific instruction will go, and calculate how many instructions go to a specific port, and calculate manually the number of cycles a single iteration will take. But I think you don't want to do that. And actually, there's another, there's a great tool to help you analyze the throughput of a particular code. It is a tool that comes with the LLVM CRAN compiler called LLVM MCA. That stands for Machine Code Analyzer. And it is given a code sequence. And given a code sequence, it shows latency and dispatch port of each instruction. And based on the latency and dispatch ports, calculates the number of cycles a single iteration necessarily takes. But it is done under some simplifying assumptions. So it is totally a static tool. It doesn't actually run the code or doesn't simulate the very details of the data you are, for example, operating on. So it just looks at the instruction sequence. So as such, it needs to make some simplifying assumptions. So the one assumption is that the code sequence you are given repeats many times. And it cannot reason about, for example, the code containing branches, and the branches sometimes go to this label and another time going to another label. So this kind of complex code cannot be analyzed. So basically just a straight line of code repeating many, many times. So another simplifying assumption is it assumes there are no cache misses. It is actually a big limiting factor that makes a huge gap between what this tools tells you and what actually happens on the machine. But then, nevertheless, it's very useful tool to analyze, the throughput limit that purely stems from the processor, not memory. And another limitation is that it assumes there's no dependency through memory, which is that, so actually when you perform a load instruction, getting some data from memory, the data you are getting is maybe produced by an earlier store instruction, right? And if this earlier instruction is executed very recently, then the load instruction may need to wait for the data written by the store instruction to become available. But this tool does assume that there are no such cases. And then there are no branch miss predictions. So those are factors that dynamically affect the performance of the actual program are sort of ignored by this tool. And nevertheless, it is a very great tool to help you analyze the innermost straight sequence of instructions, where sequence of instructions without branches in practical terms. So this is what the output looks like, and this is how you actually use it. So first, you generate assembly code from your C program like this. So you just give this -s option. And in the exercise, you have been looking at the assembly code in earlier exercises, right? So you should be somewhat accustomed to using it. And in the assembly code, you find the loop you want to analyze, right? This can be done by inserting some assembly comment in your C program. And after you find the innermost loop in the assembly code, then you insert these two comments. Well, so to put this LLVM MCA begin at the beginning of the loop you want to analyze, and LLVM MCA end at the end of the loop you want to analyze. And give this program, assembly program, to this two LLVM MCA. Then it shows the latency of each instruction used and the dispatch port used by each instruction. So you don't have to manually look up the processor manual or whatsoever to know which dispatch port is going to be used by each instruction. And it also summarizes how many instructions use each of the dispatch ports. Based on this number, you can calculate many lower bounds of the number of cycles a single iteration takes. And you can give us many options, but this timeline option is particularly useful. It shows, well, so I'm going to demonstrate it shortly, but it shows when each instruction is going to get decoded, dispatched, and actually executed and finished. So this one is particularly instructive. So just as an example, rather than showing this in the slide, I'm going to demonstrate it actually. So For example, this is the piece of code we have been talking about, right? So just doing x plus b. And this is the assembly code generated from this piece of code. And this is the innermost loop in the assembly level. So how did I find it? So I just put this begin loop and end loop label in the original C source code, and I just search for this begin loop comment in the assembly code, and the loop should be around that label. So now I identify the innermost loop is these instructions, right? So this jump instruction goes to this label, right? Sorry, this label. So the beginning of the loop. So let's say we want to analyze this loop. Then I just say LLVM MCA begin here and end here. And you have ILP rec1.s. So I just give this code. To this tool, then it shows you something like this. So it shows a number of information, but basically it calculates the number of cycles it takes for 100 iterations. You can change this number, but what this particular analysis tells you was that to execute the piece of code I have given 100 times, it will take 3,200 cycles, which means it takes something like 32 cycles per iteration. 32 cycles per this iteration containing 8 FMR operations that are dependent on each other, right? So the reason why you see 8 FMR operations within a single iteration is that the compiler was doing something smart. So something called loop unrolling. So it executes 8 iterations per a single iteration in the assembly level. So you have actually 8 FMR operations, FMR instructions that are dependent on each other. So remember that a single FMA has a latency of 4. So if you have 8 of FMAs that are dependent on each other, then you take 32 cycles to go through this instruction once, right? So the result looks pretty accurate, right? And another thing that is often useful is this resource pressure by instructions. So this table tells you which execution port is going to be used by each of these instructions. So actually, this tool thinks that this processor has 12 dispatch ports. But it somehow knows that all FMR instructions need to go either port 2 or port 3. And this particular instruction almost always goes to the port 2. And in the same, hopefully in the same cycle, the next instruction can use the other dispatch port that is capable of doing floating point operations. Right. So, but by this, by this result, you can, understand that these 2 ports are probably ports for executing floating point operations. For example, you can see this integer add instruction is going to this port, so completely separate from floating point dispatch ports. And here's a jump instruction that is taken care of by this execution port. So in general, this gets far more complicated, right? So, but with this tool, for example, you can understand that, well, so if there are no dependencies or whatsoever between these instructions, well, it's actually there are dependencies, but just for the sake of discussion, assuming that there are no dependencies among these instructions, then the minimum number of cycles it takes to execute a single iteration will be 4, right? Because, well, so this port takes something like 4 instructions per iteration. And this is another port that takes something like 4 instructions per iteration. Right, so the minimum number of cycles this iteration necessarily takes in terms of the throughput is 4 cycles per iteration. Right? But of course, like I already said, this particular loop is far more severely limited by the latency, which is described here, right? So, but just by looking at these results, you can reason about how many cycles it's gonna take. So one iteration takes. And another very useful result is shown by this timeline option. So this one is particularly instructive. So well, actually, it is showing what exactly happens in the first few iterations. So only 2 iterations plus 3 instructions, right? So just the first 23 instructions or so. So this describes what happens throughout the lifetime of this particular instruction. So this D is the decode time, the point in time this instruction gets decoded. And E represents the duration in which this instruction is being executed. And this large E is the time at which the result becomes available to the following instruction that depend on it. Right, so you have this instruction and the next instruction that depends on the earlier instruction. So that's the reason why the second instruction needs to wait until the earlier instruction produces its result, right? Well, actually, this instruction was actually decoded much earlier than it is actually starting the execution. So the execution can start only after its operand becomes ready. So likewise, for example, this third instruction needs to wait for the result from the second instruction. That is precisely why this instruction gets started only after the second instruction produces its result. So this way you can very easily and vividly understand why this instruction sequence runs only as fast as 4 cycles per FMA. And of course, you can see the effect of, for example, having multiple variables updated in a single iteration just by running this tool. So it is very useful, and it is definitely something you wanna master through this the next exercise. Okay, so this is what I have just shown. Yeah, the final section of this chapter is about this. So how to get fairly fast matrix multiply using yes, many of the things I have been talking about in the last few weeks. And this is precisely what the next assignment is going to be about. So I guess, so rather than starting to speak about this right away, I guess I wanna just give you some time to look at the next assignment, PD08. So the assignment is precisely about this. So after giving you some time to work on that, looking at the Jupyter notebook and hopefully working on that, I'll come to this slide. So so let's have some time to work on the next exercise, which is about this one. So PD08 ML. So until, let's say, until 8:05. No. So 18:05. So 6. So 5 minutes past 6 o'clock. And it's going to be your next assignment you're supposed to submit. So it is basically putting many things you have learned recently together into the actual useful program, which is matrix multiplication. Well, so I got this question about this PD08. So PD0 is with GPU, right? So no. It's purely about CPU. So where did I get that? I mean this to be totally about CPUs. Okay. So let's resume the talk. But before I get started, so I'm glad to hear from you of this comment. It's a Christmas present for us. It's exactly what I meant. So just spend the day or near the end of the year on something else. So I hopefully make the teaching material available here. So so like I said, so this is going to be your next assignment, and so the reason why I'm doing this is, well, it is a very good example to which you can apply the important concepts you have learned recently, like vectorization and instruction level parallelism. So by combining all these things, you can make something useful much faster than it naively is. So that's why, I'm asking you to do this. So initially, you were given the very straightforward, not vectorized, not taking advantage of any ILP, like this. So it's just a very straightforward matrix multiplication code, right? So I think you are familiar with it, but I get to this in the slide. And well, your task is basically to make it faster, and using things you have learned recently. And I gave some pieces of code so that you can just learn it without any coding. So you can just run the very basic code without any coding. So just execute all these cells and compile it and run it. And so without any argument, so it performs the very small matrix multiply of m being 8, n being 32, and k being 192. So what is m and what is n? I'll get to that in the slide. But anyway, it's very small matrix multiply. And it repeats the same matrix multiply so many times. In this particular case, this number of times, so that it performs approximately 1 billion FMAs in total. And it reports performance, like the number of core cycles it took. And it also calculates the average FMAs per core cycle. These things. So you can make this thing faster by what you have learned. So in the beginning, you are asked to reason about the performance of this particular basic code. So why this basic code takes that many cycles? So that's actually quite important before you dive into making it faster with whatever method you are aware of. So actually, the reasoning about the performance and understanding the performance is far more important. In a way, it's far more important than knowing how to make it faster. Where often you end up with something actually that is very irrelevant for a given piece of code. So analyzing the performance and understanding the performance is, generally speaking, far more important in practice. So you are asked to do that. And then you apply vectorization or SIMD. So this is the first coding exercise. So you just modify this piece of code to apply SIMD. And again, you are asked to reason about the performance of this SIMD code. And then you are asked to apply the concept ILP, so instruction level parallelism. and do it and get a very great performance. That's how this notebook goes. And it also has a section about the LLVM MCA tool I talked about. So with this tool, you can understand why the code you actually ended up performs only so fast, or why it is so fast or so slow. Yeah, so you asked to analyze the loop with LLVM MCA. And if you have some time, so it's optional, but if you know how to do it, you are asked to further close the gap between the real peak performance and whatever you have after this problem. So simply applying SIMD and ILP. So you're actually getting fairly good performance, but there are some gaps left. So closing this gap takes more careful analysis, for which this LLV and MCA will be of great help to you. So that's what this notebook is about. So in terms of the coding exercise, you are asked to do only two things. So one is vectorization, and the other is applying ILP. So, and so this is indeed a very great exercise. So far I've been only talking about the performance of the processors, purely from the viewpoint of processor. So without talking almost at all about why you want to do that. So almost at all talking about the useful application, so to speak. So matrix multiplication, albeit being somewhat simple, it is indeed a very useful building block, especially for deep learning nowadays. So I guess, I hope you enjoy this exercise. And with that said, so let me get back to the rest of the slides. So the final section of this chapter, as well as your next assignment, will be about this developing near peak flops matrix multiply. Well, hopefully in a very disciplined and straightforward manner. So disciplined meaning that so you know why this piece of code performs only so fast or only so slow. So rather than just applying whatever you come up with that might make this matrix multiplication faster. So you apply a particular methodology, knowing that what kind of end result you should get. So this is what I mean by disciplined way. So anyway, the goal is to develop a single core for now. Well, so extending to the multi-core is not very difficult, but for now, it's a single core matrix multiply that runs at fairly good flops on isolate processor you have. And like I said several times, it is a great application of the concept you have just you have learned recently. So SIMD and IOP. So specifically, we are developing a code that does this. So C equal A multiplied by B plus C. So in a way, so in other words, it's like a C plus equal A by B, right? And as you know, so there are some constraints about the size of the matrices, right? So the number of rows must be the same between C and A. The number of columns must be the same between C and B. And the number of rows of, the number of columns of A must be equal to the number of rows of B, right? So this constraint can be more nicely represented by placing these three matrices in this way, right? So A next to C, B on top of C, right? So just to signify that the number of columns must be the same between B and C. The number of rows must be the same between A and C. Also, these two sides must be the same, but this cannot be nicely represented in this picture too. But anyway, so I'm going to use this illustration when I talk about how you perform matrix multiplication. And so I'm going to make a few assumptions for convenience, so without losing any generality. So specifically, we're going to add some assumptions about M, N, and K, more specifically, that they are, when necessary, multiple of certain numbers. So especially when, for example, when you apply vectorization, you want to assume that, whichever M, N, or K along which we apply the vectorization should be a multiple of the number of lanes in a single vector, right? So otherwise, it's that the coding becomes just a bit tedious. So you can do that, but in the exposition, I'm going to ignore that, right? So I'm just making an assumption that, for example, when necessary, M is a multiple of the number of lanes, or N is a multiple of the number of lanes, things like that. And we also assume that matrix sizes are conveniently small. The reason why I need to introduce this assumption is that if the matrices are very large, they do not fit in the cache. And the cost of the matrix multiplication may be affected by the cost of getting data from memory rather than what happens inside the processor. So it's actually a very important topic in its own right. But for this exercise, we are focused on how you optimize things that happen in the processor without worrying too much about how you get the data from the memory. So for which the assumption that matrices are very small are actually very convenient. And also the reason why I introduced this assumption is that multiplication of larger matrices can be built on top of this. So once you have very efficient matrix multiplication for small matrices, so large matrix multiplication can be implemented by using this as a building block. So with that, let's get started. So this is what the baseline code actually looks like and what the baseline code actually does. So it's not vectorized at all. So it is just a triply nested loop that you all should be familiar with. It's just a straightforward implementation, just following the definition of matrix multiplication. Just a Cij is the sum of Aik multiplied by Bkj for all k's, right? So this is exactly what the matrix multiplication is in the mathematics textbook. And what happens in the innermost loop is it runs this K so in index, right? So if you change the K, what happens on A is it works on the next column, right? So if you increase the K, the element goes to right in this picture. And what happens on the K, so what happens on B is if you increase K, the next element is just below the current element, right? So overall, what this innermost loop does is take an element here and here, multiply them, and accumulate it here. And the next element, get the next element here and here, multiply them, and accumulate it here, right? So this is what this innermost loop is doing. And if you actually run this code, you see something like this in terms of the performance. So I just I can just show a demonstration. So just for the sake of clarity. So I'm just executing all these cells and execute the actual executable. So you get something like 0.35 FMS per core cycle. So what is the goal? So the goal is make this number something close to 32. So it's still something like 100 times slower than what we like to be. But anyway, so the important thing is how to reason about this particular performance. So if you just take the reciprocal of this 0.35, so 1 over 0.35, you can get the number of cycles per iteration. So the number of cycles per a single FMA, right? So which is something like 2.8. So what you actually expect from this code is actually slightly different. So it's close to 2.8 clocks per iteration, but it's actually slightly different. So like I said, so essentially, so what happens in a single iteration of this innermost loop is a single FMA. Well, precisely speaking, it is getting an element of A, probably from memory, and getting an element from B, probably from another location in memory, and doing FMA. But essentially, it's FMA. And the problem of this code is, like the one I have been using in the beginning when I talk about this IUP thing, it is all the iterations of this innermost loop update the same element of C, right? So no matter how you optimize this innermost loop, well, the fact remains that it is updating only a single variable. So in a way, it's very similar to what we have been talking about before, right? So it is in a way very similar to what is happening here. So you keep updating, so you keep applying FMA on the same variable. But the dependency pattern is somewhat different, right? So it's more like C equal A by B plus C. So it's not necessarily that the same C is used here, but the same C is used here. So for this reason, when the actual expected performance is something like 4 clocks per innermost iteration. What we actually witness is somewhat better than that. The reason why it's somewhat better than what we expect is not hugely important, but the reason why it's slightly smaller than 4, which we should expect based on what we know, is that there are actually some overlaps between iterations. So there are some overlaps between iterations updating one element of C and iterations updating the next element of C. So the recent superscalar processors are so good at decoding execution very ahead of what the actual execution is happening. So while one particular execution of this innermost loop is happening, the execution, that's the instruction decoding and fetching, goes ahead of it, and it starts executing, updating the next element of C. So there are some overlaps between different elements of C. So that's the reason why it's somewhat faster than 4 clocks per iteration. Well, just as an evidence of that, you can change the matrix size. Well, actually, you can specify M, N, and K as the first 3 parameters of this command. So I'm just making both M and N 1, so that there's only single element of C. Yeah. So C is just a 1-by-1 matrix. So then what this code is doing is precisely just a single dot product, essentially. So then what happens is that it reports almost like a 0.25 FMS per core cycle, which is equivalent to, say, 4 clocks per iteration, right? So this precisely matches what we expect, right? So the slight difference between 4 cycles per clock, I'm sorry, 4 cycles per iteration and 2.8 cycles per iteration do not matter very much. But just for the sake of understanding. So the achieved performance is something like, well, this many FMAs and this many cycles, something like 0. Actually, it was 0.35 FMS per cycle. Anyway, so it's very limited by. Well, first of all, it is not using SIMD at all, and the other reason why it's so slow is it is not taking advantage of ILP almost at all. So it is updating only a single C element at a time, right? So we are going to discuss how to apply SIMD and how to apply then ILP. So first about SIMD, or vectorization. So when you think about how to apply vectorization, well, the only question you need to answer is, okay, so which loop you want to vectorize? So along which dimension you want to execute several iterations at the same time? So it can, in principle, be any. So all these 3 loops are, no. So well, at least the outer 2 loops are completely independent, right? So the innermost loop is dependent on each other through updating the same C element, but they are reduction. So actually there are some ways to vectorize it too. So actually you have 3 choices. You vectorize it along this I loop, J loop, or K loop. But after you think about which one is most profitable, what the only reasonable conclusion is actually to vectorize along the second loop, which is J. Do you know why? Well, so you want to think about yourself, but so when you vectorize along this dimension, so J loop, then what happens is something like this. So you take several elements of C in the same row, and you take the several elements of B in the same row again. And then you want to multiply this one and all elements of this vector and accumulate the multiplication into this vectorized C element. And it is most efficient. So if, on the other hand, for example, you vectorize along the outermost loop, what happens is that you operate on a number of elements along the color of A. And also you work on several elements along the color of C. And you get a single number from B, and you multiply this scalar with this vector and multiply them and accumulate them into these elements. So the difference is that whether the number of color the number of elements you want to work on at the same time is put along the row or color. And well, it depends on how you lay out the elements of the matrix. But in what so-called C conventions, but these elements are put in the contiguous addresses in the address space. On the other hand, contiguous elements along the color are actually not contiguous in terms of the memory addresses. So, for example, if you wanna fetch several elements along the color of a matrix, well, actually you wanna use you cannot simply use the vectorized SIMD instruction. So you have to resort to more complex instructions like gather instruction, which is actually far more costly than just ordinary vectorized load instruction. So by vectorizing along this J loop, well, so you do not have any issue like this. So all the elements you wanna work on at the same time are contiguous in the address. So this way you can vectorize it, and it's your exercise. So I'm going only speak. I'm speaking only about the high level strategy. So after you have done that, you can actually run the code, and you're gonna get you're gonna see something like 16x speed up pretty easily. So I'm sure you are pleased to see that happen. But the kind of performance after applying this SIMD is still away from the ideal peak performance. And the reason is actually the same as before. So even if it is vectorized, the fact remains the same that, okay, so let me explain using this code. So in terms of the pseudo code, the vectorized version looks like this, right? So you take L elements of B at the same time. You update L elements of C at the same time. But even if you use vectorized instructions in this way, the fact remains the same that you are updating only a single C element at a time. Also, to be more precise, only L elements at a time, or only a single vectorized element at a time. So it is still limited by the latency. So the innermost loop runs only as fast as something like 4 cycles per iteration, right? So it's still far from the peak performance, which is 2 FMAs per iteration. So how you can improve it? So like I said, so the only way is to increase parallelism. So fortunately, so you have so many elements you have to work on, right? So you have so many C elements, right? So why do you just updating only a single vectorized element at a time? Why don't you do something like this, right? So you take, for example, 4 vectorized elements, and the innermost loop, you update 4 different elements of C, like this. So this is what this slide illustrates. And there's some so the details you need to understand to know why this piece of code doesn't get quite peak performance. So there's some reasons why it is still slightly away from the peak performance. And this slide talks about this, but I will just leave it for your exercise. And this slide also talks about a better strategy that, well, at least in theory, should get very close to peak performance. Well, so I leave it to your exercise. And yeah, with that, you can actually get something like 80% of the peak performance, which is pretty good, considering the simplicity of the code. And this is exactly what, yeah, I want you guys to experience in the next assignment. So I think I'm running out of time. So do you have any question? Okay, so if you don't have any questions, so I will. So let's finish today's lecture.